I believe this was the most challenging problem in the contest. So this problem is called potion farming. So basically, yeah, so there's there's a series of n rooms that are connected by n minus one edges. So it's basically a tree. And then you can think of the tree rooted as at one, and you can explore the map by making a series of traversals. So um, you start the traversal from room one, and you go to any other room, and the map is complete once um, every room is visited by at least one traversal. And the main goal is to complete the map and the minimum number of traversals. So I'll get to the rest of the problem, but part of the problem is finding the minimum number of traversals. So let's just discuss that first. And you have uh, so for your constraints, I'll explain the rest of the problem later, but you have n is at most 10 to the 5, and basically from the root, you want to explore everything in the minimum number of traversals. So a few observations. So let's say a traversal starts from the root to some vertex u. So one observation is it doesn't worsen your answer if you keep traversing. So basically, you can keep traversing until it reach a leaf, until you hit the leaf. Observations. And then basically, so each traversal, basically if you hit the same leaf, it's kind of a waste. So you want to hit a different leaf each time. So this implies that number of traversals is equal to the number of leaves. So basically, given your tree and there's a bunch of leaves, each traversal, it's optimal to end at a leaf. So the total number of traversals is going to equal the total number of leaves, right? So so part of the problem is like knowing like what the minimum number of traversals looks like. So let's continue reading the problem. So your secondary goal is to farm as many potions as possible. So before a traversal begins, a potion will spawn at some room in the map. And you can pick up the potion by visiting the room that the potion spawned in at the current traversal. And if you don't pick up the potion, then it'll disappear. So given the minimum number of traversals, uh, you want to collect the maximum number of potions, right? Um, yeah. Uh, yeah. So basically, like you know that you'll finish in T traversals. So consider where the potions will be from times 1 to up to T, right? And you know what the optimal traversals for those T optimal paths for the T traversals is? It's just path to the leaves, to the leaf. So basically you want to order these traversals so that so that you hit the potion at each traversal. So basically, like from times 1 through T, there'll be a potion at a different location, and you want to maximize the number of traversals that'll pass through that potion, right? So basically, if you start from the root and a traversal goes to the leaf, then you're going to hit the potion if it's in the path to that leaf, right? So basically, yeah. So basically, you reach a potion if this leaf is in the subtree of that potion, right? So basically, you want to match potions to leaves. So this problem reduces to matching potions to leaves. Yeah, and you can argue that it's best. Yeah. So let's just say we have like a leaf here, and there's two potions that are on the path to the leaf. Uh, it's always better to match the lower potion to the leaf, than the higher potion to the leaf. Because if you match the higher potion to the leaf, um, uh, either you match the yeah. So either yeah. So basically, you either you match the lower potion to a different leaf, in which case you can get a similar solution uh, by swapping and doing this. So this is something in greedy algorithms called exchange arguments. Basically, if you swap something in a suboptimal solution and things will only get better, then that's how to show something is optimal. So basically, suppose that the one at the top was matched to the leaf. If you swap, and if you suppose the one at the bottom is matched to a different leaf, then if you swap them, the solution won't get worse. Um, and I guess the other case is where the one at the top, uh, the one at the top is matched to a leaf, and this is matched to nothing. Then if you swap, then you can match this to the leaf, and you have more options to match to the top too. So you could potentially get +1, right? So the optimal strategy uh, is to match uh, lowest potion to leaf, right? So basically what we want to do is um, like one way we can do this is iterate through potions that are from deepest in the tree to highest in the tree. From lowest to highest. And then, uh, yeah, so when you're at your potion, just match to any leaf in the subtree. Yeah, so this will be like naively, if you just iterate over the potions that are from lowest to highest, and then match to any leaf in the subtree. So you're iterating over like O of n potions, and then the time to find a leaf, which is like a depth first search, will be O of n. So this will be O of n squared. So you can pass the subtasks using this. I think yeah. So it's like this n less than or equal to 1000 subtask. Um, but we can do better. So the idea is you can do this recursively. So you want to solve for a vertex, and then you match the potions in its subtrees to their leaves. So basically you recurse over all these and you match their potions to their leaves. And once you recurse, you keep track of the number of remaining leaves. Yeah, so basically you can solve for this subtree since we know it's optimal to match the deeper potions uh before the higher positions, and just match these to their leaves, and then go up the sub when you're and then you can return the number of leaves that are remaining. So you can do something like int solve int u for the child um uh, num leaves plus equals solve v, and then yeah, so if and then match the potions from u. U, and then you might need to decrease num leaves based on if there's potions at U, and then you return num leaves. Yeah, so the idea is you can match the potions from lowest to highest. And we can do this recursively by matching the potion in each subtree to leaves. And you can recursively find the number of leaves if you optimally match the subtrees. And then if there are potions that are at location U, then you can match these to any arbitrary leaves. And then like decrement num leaves, depending on how many potions you match, and you return num leaves. Yeah, so let me summarize. Yeah, so you can find the minimum number of traversals because each traversal will hit a leaf. So it's going to be the number of leaves. Um, and then the problem reduces to matching the potions to the leaves. Um, and we can show the optimal strategy is to match the lower potions first. Uh, and since it's optimal to match the lowest potions first, then we can do this, we can solve this recursively where we match all the potions in our subtrees. And then we get the number of remaining available leaves and then match our potions to those leaves. Yeah, so that's the solution to problem 2. Yeah, any questions? I'll go to problem 3. Yeah, I guess, yeah, they're equivalent. Okay, let's go to this problem.